Hello ladies and gentlemen, my name is cikm2022 and together with my colleagues Pavel Kopil and Irena Hulbova, we would like to present you cikm2022, a tool for modeling and evolution management of multimodal data. This video is divided to three parts. First, we will introduce the multimodal data and explain why it's needed and what challenges it creates. Next, we will describe the main concepts of our proposed approach and show how it overcomes the challenges of the multimodal data. Finally, we will do a practical demonstration of the proposed tool on some real-world examples. Multimodal data emerged as a solution to great variety of the big data. It combines many different data models such as relational, document, graph, and more. In order to handle it effectively, we need tools that would allow us to model it and, later, to evolve the model so that it can keep up with the changing data. Such tools already exist for the single model data, mainly for the relational data. However, there are several reasons why modeling of multimodal data is much more challenging. Just to name a few, different models have contradictory features, like schema-full and schemaless models, or aggregate-oriented and aggregate-ignorant ones. The resulting unified model has to contain complex structures, like cross-model integrity constraints. There are also many ways how to combine multiple models. We can use embedding, references, redundancy, or all of their possible combinations. Additionally, multimodal databases engines are not standardized in any way, in contrast to, for example, SQL engines. To sum it up, we need a tool with the following properties. Its primary goal is to provide a platform-independent, high-level schema that unifies any number of different data models. Using the schema, we would be able to treat the models as one for the purposes of querying data, adding new kinds, and so on. The underlying concepts of the tool should be general enough so that it will be able to contain all currently used data models, and extensible enough to enable additions of other models in the future. It should also support all types of their possible combinations. We have already established that the tool provides some kind of an abstraction over various data models. It would be therefore great if it served as an abstraction also over particular database applications, so we do not have to work with each of them individually. As is in the case of data models, the tool should support all popular database systems. Lastly, the tool should be both designed and implemented to be as efficient as possible, so it can process large amounts of data. According to these requirements, we created the cikm2022 framework. It's based on category theory, which is a really abstract branch of mathematics. It allows us to define the unifying schema as a category, EI, a tuple of objects representing both kinds and their attributes, morphisms, representing connections between the objects, and the composition operation over the morphisms, allowing us to construct any complex connection from the basic ones. Therefore, the unifying schema is called schema category. Simply put, we can imagine the schema category as an oriented multigraph. Let's illustrate it on an example. Here we can see an ER diagram featuring customers and their addresses and friends. The diagram can be easily transformed to the following schema category. Of course, this is just a simplification. In reality, each object from the schema category bears additional information, such as keys, called identifiers, and integrity constraints. Also, the morphisms specify cardinalities of the relations they represent. Now, let us describe the overall architecture of the framework. The schema category is the backbone of the platform-independent layer. It's a subject to evolution management, and it enables additional operations, like querying and data migration. The platform-specific layer contains various logical models. Each one of them is made for a specific database application e.g. Neo4j, MongoDB, etc. So it can allow us creating platform-specific structures, like arrays or nested objects. For each module, there is one so-called mapping that maps the module to the schema category. With this basic architecture, we are already able to perform the data migration. First, we create the logical modules corresponding to the actual data and the schema category that unifies them. Then, for each logical module, we use its mapping to import the corresponding data to the platform-independent layer. Finally, we create the output logical modules and, using their mappings, we export the data in the form of DML statements. The main takeaway here is that we do not need to specify mappings between the logical modules. We only have to specify mappings for each logical module to the schema category. Here you can see the schema from the previous examples. There is a customer with attributes like name and surname. There's also the address. This schema unifies two logical modules, one for the customer and the other for the address. The logical module for the customer is a relational one, so we can visualize it as a table. As we can see, all its 4 columns are mapped to the 4 attributes of the current customer. The model for the address is also relational. The last 3 columns from the table correspond to the 3 attributes of the current address. The first column represents a self-identifier of the address and is therefore mapped directly to the object of address itself. This identifier also acts as a link between customer, ei the column address from the customer table, and the address. Note that this schema category isn't fully covered by logical modules. The object friend isn't contained in any one of them. Nevertheless, we can still use the already mapped parts of the schema, ei the customer, the address, and their attributes, meaning we can import data to them or export data from them via the current mappings. However, in order to use the information about friends of the customers, we would have to create a corresponding logical models first. So we are able to model multimodal data. We can also import the data to and export it from the platform-independent layer. Now we need a way to modify the conceptual schema and, accordingly, the logical models and the actual data. We do so by the so-called schema modification operations. We have defined several operations for adding or deleting objects, morphisms, identifiers, or integrity constraints. There are also more complex data transformations, like changing cardinalities of the morphisms and moving or grouping of the objects. In general, the operations affect primarily the schema category layer, since this is the level of abstraction we expect the user to work on. The operations are then propagated to the mappings and, potentially, to the logical modules and the data instances. If they are propagated only to the mappings, we call them light operations. If they affect also the logical models and the data, we call them heavy operations. Note that the propagation is done eagerly. For the mappings and the logical modules, it sometimes can't be done automatically, meaning an additional user input is required. However, the propagation to the data, which is the most tedious part by far, is fully automated. Now it's time for a practical demonstration. Here we can see an example schema category. There are kinds customer and order. Each customer can have any number of orders. An order is therefore identified by its date and the ID of its customer. An order consists of multiple order items, which group items with quantities and prices. The schema category might represent a schema of a business application. Let's imagine that some part of the data is stored in a document database, like for example MongoDB, and the other is stored in a relational database, for example Postgres. So we have two logical models, and for each one of them we have one mapping. The first mapping is centered on the kind order, and it's document with customer ID, date, and an array of items. Each item has its label, quantity, and price. The other mapping is just a simple table with ID and name of a customer. Of course, there can be any number of attributes, but since it's a relational database, nesting is not allowed, so all attributes have to be on the same level. Let's look on some simple data so we can better visualize these mappings. As we have said, the orders are stored in a document database, more precisely MongoDB. So here we have an order with customer ID 1, some date, and 2 order items. There's another order for customer with ID 2, and yet another order which is for the first customer again. The customers are stored in a Postgres database. So here we have some simple data. The data was already loaded to the databases. Now let's see how we can import it to the tool AI to its platform independent layer. For each logical model, we have to create a job that imports the data to the system. We want to import data, so we choose model to category. Now we have to select mapping, so let's select document order, and we choose name for the job. The results will be seen in the instance category. Now there's nothing to be found. So let's run the job, and now we should be able to see the imported data. However, there's nothing about the customers. There are their IDs, because they are included in the orders, but there aren't their names. There also isn't the ID of the third customer, because Carol doesn't have any order. So now we have to import the customers. We create another job. We run the job, and we should be able to see the customers. As we can see, their names were linked to the data imported from the order document database. Now, let's export some data about the customers, but in the document form. We select the MongoDB, and as root object, we select the customer. Now we can add some attributes to the customer. So, for example, let's start with the name. We select name. It's a simple property, and we keep the name. Now we may want to add an array of all the orders the customer have ever done. So we select order. It automatically continues with a complex property, and we rename it to all orders. Then we can add attributes for all orders. Let's select the date. And let's add the names of all the items in the order. Lastly, we have to select the name of the mapping. So, for example, and the mapping is finished. Now we can export it, so we create a job. This time we choose category to model because we are exporting the data. We create the job and we run it. The results are displayed here. So this is the exported model of customers, and it's a collection of MongoDB statements. As we can see, all 3 customers are here. So, this was a really simple demonstration of the proposed tool and also an introduction to the MM-Evocat framework. There is, of course, much more to be shown, but we didn't want the video to be too long. For conclusion, let's sum up the main advantages of our approach. We have created a robust, multimodal data modeling framework that can be used to unify all currently used data models. It's based on category theory, and its architecture allows us to see high-level conceptual schema of any given system while keeping all its low-level details. The tool also enables evolution management of multimodal data. We have seen an example of cross-model data migration, which changes logical models without changing the conceptual schema. Then there are the schema modification operations, we change the schema and propagate the changes to the mappings and or to the logical models and consequently to the data. So that's all for the demonstration. Thank you for your attention, and if you have any questions regarding the MM-Evocat framework or if you are interested in the project, don't hesitate to contact us. Again, thank you for your attention and have a nice day.